Think wall. Is the area clear? Okay. The video and audio. Right. So, any queries from anybody on the previous class on rings? What we have discussed? Here we discussed about how to show that a given set is a ring, and some problems based on that. What is meant by integral domain, Boolean ring, their properties, etc., etc. Say. So in today's class, again we take some of the previous concepts. Then we discuss about subrings and ideals and their properties. That is the objective of today's session. So I request you to recollect what is meant by an integral domain. The definition is given by, you have to take a commutative ring with unity and having no zero divisors. So this is the definition of integral domain earlier. And we discussed some other things also, that so if you consider a field, every field is integral domain. This part we already discussed. And what you think about the converse is, every integral domain a field? For this, the answer is no. The very simple example is nothing but, consider the ring of integers z plus dot. It is just an integral domain because it has no zero divisors. And if you talk of multiplicative inverse for non-zero elements here, so whenever you take a number, say 3, the multiplicative inverse is 1 by 3, which gives the value 1, but 1 by 3 does not belong to Z. So inverse property fails in the set Z, so it remains as only integral domain but not a field, right? This is the problem. Clear for all? Yes or no? Any questions for anybody? All right. Now, the other one is the possibility for an integral domain to become a field is, it must be a finite set. If you take a finite set which is an integral domain, then it will become the field. Okay? Now let us prove that part. Shall I proceed? Are you getting any difficulty in correlating the previous concepts and the current session? Tell me. Or do you have any lag between the video and audio in the class? Do you have any? Are you with me? Yeah. Are you getting any lag? Thank you. Because based on your response, then I will continue the class session, because I get doubt-minded that are you able to follow the session what I am telling now? That's the question from my side, right? Because if you didn't give your response, I am unable to cope with the class situation, because it looks purely theoretical, right? That's why. So here, the result what we are discussing about is every finite integral domain is a field. So let us prove this result. So from the very definition, let us take a set that D is equal to 0, 1, A1, A2, so on, AN is a finite integral domain with n plus 2 distinct elements. So here A1, A2, so on, AN are any values in the integral domain you can consider, the total number of values. 0 stands for additive identity and 1 stands for multiplicative identity. So these are not simply 0 and 1. 0 stands for additive identity and 1 stands for multiplicative identity. So I have considered an integral domain with exactly n plus 2 elements. So here my claim is it is a field. So as you know what is meant by a field and what is meant by an integral domain. So comparing these two terms, I mean the definitions of field, the definitions of integral domain, then what are the additional properties D has to satisfy so that it will become a field? Can you tell? What are the additional properties D must satisfy to become a field? Inverse property. Is everyone agree for this? Any questions? Is everyone getting the idea? Why should we prove inverse only? To show that it is a field? Tell me. Yes or no? Let me write again then if you have a doubt. So, as you know, the relation between integral domain and field, it is a ring, it is also a ring, it is commutative, it is also commutative, it has unity element, it also has unity element, it has no zero divisors, it will possess inverse. This is the definition of integral domain and that is definition of field. So if you compare the properties common for both, so you have to show that it will become a field if it possesses the inverse property. Checking up the technical terms, common in the both definitions. Agree? All of you. Yes or no? Right? So, what is meant by inverse here? In this set, if you take any non-zero element, so by multiplying with other element in the same set, you should get the value 1. That is called the inverse property satisfied within the set D. That we have to show. Right? Now let us go for that. Now you consider a non-zero element in the set D. So our aim is we have to show if you multiply A with some other element, you should get 1, and this element must be in the same set. Now what happens? Excluding the 0 element, you will multiply all these elements with this value A. So what happens? You will get n plus 1 products accepted. I have taken the element A, which is a non-zero element in the set. You can take any non-zero element in these values. And excluding 0, I am multiplying all the non-zero elements with this value A. So I will get the set of products A1, A into 1, A into A2, so on, A into AN. So this is nothing but the set having n plus 1 values. Now I say that these n plus 1 values are distinct. And also they will belong to the same set as per closure law. So closure law means whenever you take two elements in the set, if you multiply them, again it will belong to the same set. So these elements are obtained like that. So by closure law, all these values will belong to D. And another thing is, I am saying that all these values are distinct and non-zero also. Right? All these values are distinct and non-zero also. For that, if you have a doubt, you can consider that, say, two values become equal. So, by applying cancellation law, you will say A is equal to AJ, which is a contradiction. Why? Because all these elements are taken in the set D, right? And all these values are distinct. Earlier you have taken that these values are total n plus 2 values which are distinct in the integral domain. So in these n plus 1 values, no two terms are equal. Another one is all these n plus 1 values are non-zero. Why? Because it has no zero divisors. So what does it mean? If you take two values non-zero, the product is also non-zero. So as you have taken A as non-zero element, 1 is a non-zero element, hence the product A dot 1 is also non-zero. Similarly, A is non-zero, A1 is non-zero, hence A dot A1 is also non-zero. Clear? So all these values are totally distinct. they belong to the set D and all these values are non-zero. That is our conclusion here. Any queries for anyone? Yes or no? Now what happens? D contains exactly n plus 2 elements. In this n plus 2 elements, you exclude 0. Then you have n plus 1 elements here. You are saying that after multiplying with A, you will get n plus 1 different non-zero values and all these values belong to D only. So what does it mean? The initial set what you have taken with n plus 1 values and the resultant set after multiplying both must be equal. That is the only possibility because all these values are belonging to D, right? So we mentioned that the set 1, A1, A2, so on, AN must be equal to the set A dot 1, A dot A1, so on, A dot AN in some order. This kind of observation you already made while dealing with group theory. Let me give a small idea that while forming the coset, say, if you have taken the set G is equal to 1 minus 1, I minus I, you fix an element I. So with this element I, you multiply all the values. So this is nothing but Ig. You have multiplied the whole set with the value I. So G and Ig both are equal. The elements are same, maybe the order of the elements will vary. Agree? In the same way, here also the n plus 1 values what we have taken initially and the n plus 1 products after multiplying with A both must be equal. That is the only possibility as per this example. Therefore, since the two values become equal, so here A1 is equal to one of the values here. A2 is equal to one of the values here. Similarly, 1 is equal to one of the values here. Therefore, there exists AI such that A into AI is equal to 1. Therefore, AI is the inverse of A. Therefore, D possesses multiplicative inverse. Therefore, it is a field. That is the solution of the result. Please check what we did so far. In a nutshell, the total result, we simply mention it as, first you take a finite set having n plus 2 elements. You exclude 0 on that. In the remaining values, you pick up an element A, multiply all these things. So here we conclude that these n plus 1 terms which you obtained recently are distinct, non-zero and belonging to D. As you have taken a finite set, the only possibility is nothing but these two must become equal. As and when they become equal, the elements on the left side are equal to elements on the right side in some order. So the element 1 must be equal to one of the elements here. So there exists an element A such that A into A is equal to 1, hence inverse property is proved because you have got the relation that A into something equal to 1. So this something is nothing but inverse. Therefore, it possesses the inverse property, hence it is a field. That is the conclusion. Any doubts? So if you have noted, then I will take the other one. Can I? Right. So we already know that what is meant by an idempotent element. It is nothing but if you take an element A belongs to R, if A square equal to A, then we say that A is the idempotent element. So why we consider this concept? Because whenever you consider an integral domain, if you want to calculate how many idempotent elements will be there in this. So let us go and find this. Let us take A is an element in the integral domain which is idempotent. So as per the definition, A square is nothing but A. So taking the values to the left hand side, A square minus A equal to 0, which gives that A into A minus 1 equal to 0. Yes, here I am talking about the idempotent elements in the integral domain. So my intention is, if you consider an integral domain, then how many idempotent elements will be there in that set? That is my task here. Okay? Fine. Right. So, as per the definition of idempotent, this is the thing you have, and this relation you will get. Agree? As we know, integral domain has no zero divisors. It means that whenever the product is 0, either x must be 0 or y must be 0. This is the property that having no zero divisors. So here it is of the form x into y equal to 0. From this you can say that either a is equal to 0 or a minus 1 equal to 0. Which gives the thing that either a is equal to 0 or a is equal to 1. So here I have taken A as any element in the domain. If you feel that the element is idempotent, then it has only two choices, either 0 or 1. Agree? A has no other choice in the integral domain. So it means that if you keep on calculating how many idempotent elements are there in the set, there will be exactly two elements. One is 0, the additive identity. Another one is 1, the multiplicative identity. So in an integral domain, always we get exactly two idempotent elements. Okay? You take a note of that. Shall I continue? Yes or no? Now, we talked about nilpotent element also. So what is meant by nilpotent? If you take an element in a ring or then you keep on raising the powers. So at a particular power, you should get 0. If such a situation happens, we say that A is a nilpotent element. Now the question is, if you want to calculate how many nilpotent elements are there in the integral domain, then there is exactly one nilpotent element. It is nothing but 0 in that set. The result is very simple. Suppose you have taken that A belongs to D is a nilpotent element. Here D is integral domain. So let us take an element first. Apart from saying it is nilpotent, and let us take that this is a non-zero element. So you take a non-zero element in the integral domain. Now, if you start raising the powers of A, so if you consider A square, it is nothing but A dot A. And I say that it is not equal to 0. Why? Because since A is a non-zero number, the product of two non-zero values is non-zero because it has no zero divisors. So if you consider A cube, this is A square dot A is also not equal to 0. If you consider A power 4, it is A cube dot A, this is also not equal to 0. You keep on calculating. So whatever the power you consider, always the result is not equal to 0. Because it has no zero divisors. So if you take that any non-zero element A in the integral domain, how much power you raise for it, it is always not equal to 0. You will not get such type of situation like A power n equal to 0 for some n. That won't happen here. Therefore, there you cannot get any nilpotent element. So the only nilpotent element is nothing but 0. Because 0 power 1 gives 0. Okay? So there will be exactly two idempotent elements in an integral domain and one nilpotent element in the integral domain, which is nothing but 0, the additive identity. Okay? You take a note of that. After noting, please inform. In the previous class also, we discussed another important context, that what is meant by the characteristic of a ring. and we discussed some problems also on it. Can you recollect the definition of characteristic of a ring? Say, it gives what? Yes, it is the least positive integer p such that p into x equal to 0 for all x in the ring. Agree? Now, if you talk about an integral domain, what could be its characteristic? If you consider an integral domain, what could be its characteristic? So here, the solution for it is either 0 or prime number. This is the answer for it. The characteristic of an integral domain is either 0 or prime number. So for some integral domains it is 0, for some it is p, a prime number. Now let us go on to prove this. Can I? Okay. Let us prove that. So you take that D is an integral domain and take P not equal to 0 is characteristic of D. If you say that characteristic is 0, then there is nothing to prove. So if you feel that characteristic is non-zero number, then you have to show that that non-zero number is nothing but a prime number. This thing you have to show. So to show that that characteristic is a prime number, since there is no direct proof available, we use the technique of contrary way or the method of contradiction. So what it means? We assume that P is not a prime number. We start the procedure, then you will get a contradiction. So our assumption must be wrong, hence P definitely should be a prime number. Now, if possible, let P is equal to m dot n, where I have taken that P as a composite number, product of two values, where one less than m comma n less than P. So, if you take any non-zero element, then the square is also non-zero, it belongs to D. Since P is characteristic, we have P dot A square equal to 0. Please check this step. Any questions you can ask. To prove the claim, we are moving in the contrary way. So I have assumed that P as a composite number. So I can write P as product of two values. The numbers are taken as bigger than 1 and smaller than P. So if you take any non-zero element A, then A square is also non-zero because you have taken the integral domain. Since P is a characteristic, whatever the element you take in D, if you multiply with P, you should get 0. So P into A square must be 0 always. Okay? Please tell. Now, as you got a small value for P, let us substitute here. Because P is nothing but Mn. So using associative property, you can write it as so applying associative property, you can say that MA dot NA equal to 0. So since the product of two values is 0, either of the value should become 0 because it has no 0 divisors. Now let us go with the other part. Now you take 0 not equal to x be any element in D. Right? Since you have arrived at a conclusion that one of these values must be 0, let us take that MA equal to 0. So if you take this thing, multiply this value on both sides with x, agree all of you? Say. I will say the value in a different manner also. So please check on what I have written. If you take any non-zero element x in the integral domain, there you got that either MA equal to 0 or NA equal to 0. So if you assume that MA equal to 0, multiplying both sides with x, you have MA dot x equal to 0 dot x. You can apply associative property. So you can write it as A dot mx equal to 0. So here what you got? The product of two values is 0. This is one value in the product, this is other value in the product, and the product value is 0. Since it contains no 0 divisors, whenever the product gives the 0 result, either of the values must be 0. So you should have either A0 or MX0. Earlier you have started with A is a non-zero element. So the only possibility is mx0. Okay? Yes or no? Please take a note of that. If you have any confusion, you can ask. Anybody? Please understand that here MA means you have added A M times, the result is MA. Don't feel that M is a separate number, A is a separate number. Don't talk in the perception of numbers. Okay? So here I have taken a quantity A, I have added the quantity M times, because initially you have taken that 1 less than M comma N less than P. You cannot say M is equal to 0 from that. Please understand that. Because if you take that P is a composite number, this is the possibility to write P like this. Accepted? That's it. Any other queries from anybody? Are you clear in saying that mx equal to 0 at this part? Now please understand that I have taken x is any element. X is any element in D. So what happened? Mx becomes 0. So if you take any non-zero element, then if you multiply with m, it is becoming 0, isn't it? So this is a contradiction. Contradiction to what? You have taken that P is characteristic. It means that if you multiply with a number less than P, you should not get 0. So here you got a contradiction. M is a number which is less than P. By multiplying with M, I got 0 here. That is the contradiction here. Okay? Are you clear? Yes or no? Therefore, our initial supposition must be wrong. Hence, P must be a prime number, not a composite number. That is the conclusion of the problem. Please take a note of this, then I go further with the definitions and other concepts. After noting, please inform. So at this point, you can add one more thing that, as we know, every field is integral domain, and integral domain has characteristic either 0 or prime. So we say that every field has characteristic either 0 or prime. Okay? So every field has characteristic as either 0 or prime. That you take a note of that. So let us take the definition that what is meant by a subring. So from the very word, it is clear that it is a subset and as well as a ring. So whenever you consider a ring R plus dot and you take a subset in the ring R, say yes. If S plus dot is also a ring, then we say that it is a subring. Okay? So what is meant by a subring? It is a subset as well as a ring. Please understand that whenever you talk of subgroups, subrings, etc., whatever the operations you are dealing with are, the same operations are also applied on the subset. So you should not take different operations. Whatever the operations plus and dot hold on R, the same things we will consider here on S. Okay. Right. Now the question is, if I am given a subset for a ring, I need to verify whether it is a subring or not. Then what is the general procedure we follow? The usual thing, you have to verify that S comma plus abelian group, S comma dot semi group, distributive laws hold on it. So you have to verify the 9 properties for the subset S with the same operations taken on R. Now it becomes a lengthy procedure, always verifying the properties on the subset, isn't it? Yes or no? So if you talk of group theory, in order to verify a subset becomes group or not, we make use of the necessary and sufficient conditions. Can you tell the condition? Whenever I am given a subset, I should verify whether it becomes a subgroup or not. Then what test I will check on the subset? Say, for the infinite sets, generally what we will do? The necessary and sufficient conditions, I am saying that if G is a group, H is subgroup of G, then what condition we check? If you want to show that H is a subgroup of G, yes, the condition is nothing but AB inverse belong to H. All of you agree? Right. Now tell me, what is the operation on G? What is the operation on G or the operation on H? What it is? So always, by default, we prove every result and every theorem based on the notation dot, multiplication. G comma dot is a group, H comma dot is a group. So unless specified, we always talk about the operation dot. We will not take any different operation. So here, this condition says to us that whenever you take two elements, you take the first element as it is, apply the operation dot, and take the inverse for the second element. Then this result must belong to H. That is the actual criteria. So if you are verifying with respect to the operation dot, this is the condition. If you take that the operation is star, you have to say that A star B inverse belong to H. So if you take the operation as circle, A circle B inverse belong to H. Agree? Yes or no? So if you take the operation plus, so here the condition comes as A plus B inverse belong to H. So what happens with respect to the addition? What could be the inverse? Let me say I have taken the value 5. What is the additive inverse of 5? What is the additive inverse of 5? Minus 5. So here, if you talk of the operation plus, the additive inverse of B is nothing but minus B. So it means that A plus minus B should belong to H. Nothing but A minus B belong to H. Okay? Did you get the idea? How I am transforming the necessary and sufficient condition to check for the operation plus, to verify it is a group or not? Fine. Now, if you want to verify a subset becomes subring or not, we simply verify two conditions. One condition is this. This is the first condition, and second condition is A dot B belongs to S. So, apart from verifying the 9 properties, we simply verify two conditions. These are nothing but the necessary and sufficient conditions. If these two conditions are satisfied by the set S, it will become subring. Clear? The advantage of necessary and sufficient conditions is that. Now you can take one more thing, that what is meant by a subfield. The very definition is simple, that just like subring, it must be a subset and it must be a field. Here AB is nothing but A dot B, closure property. See, actually it is abelian property, right? So for abelian, instead of checking 5 properties, you are simply checking one property, because this single property is equal to the 5 properties. And for semigroup, it satisfies two properties, closure and associative. Generally, whenever closure is satisfied, associative will get satisfied, so we verify A dot B. And what is this A dot B? A and B, both values are taken in the set S. Whenever you take two values A and B in the set S, if S satisfies these two conditions, we say that it is a subring. Clear now? Right. And similarly for subfield also, we take the same thing. It must be a subset as well as a field. So, if you talk of subfield, you need to verify 12 conditions. So, what are they? With respect to plus, abelian group. With respect to dot, abelian group. And distributive loss hold. So, apart from verifying all the 12 properties, we take the shortcut that, just like necessary and sufficient conditions, what we discussed. So we verify that for all A comma B belongs to S, A minus B belongs to S. This is first condition. And second condition is A dot B inverse belong to S. So this single property is equal to 5 properties. This single property is equal to 5 properties. Whenever these two hold, distributive laws will hold by default. There is no need to verify them separately. Okay. So in this way, we prove that it will become a subfield. Are you clear? Say. Now, as you talk of the number system, what we consider Z, Q, R, C. This is subring of Q. This is subring of R. This is subring of C. The complex number system. Since it is not a field, Z is not a field, so Q, R, C are fields. So this is subfield of R. This is subfield of complex number system. So rational numbers is subfield of R. Real numbers is subfield of complex numbers. Integers is subring of rationals. Rationals is subring of reals. Reals is subring of complex numbers. Okay. If you talk of examples, this is the basic examples we can see in the number system. And you can verify these two conditions whether they got satisfied or not in those sets. You can easily verify that. Now let us go to the interesting concept, that is ideals. It has very good importance with respect to UPSC point of view, and so many questions were asked on the previous year papers. So what is meant by an ideal in general? So if you take a ring R plus dot, you take a subset in it, say I. We say that I is an ideal of R if you please take a note of these two conditions, very important conditions. Whenever you take a ring R and you consider any subset I for it, then the subset must satisfy two conditions, that if you take any two values in that, the difference A minus B must belong to I. And secondly, if you take one element here and one element in R, you consider the product A dot R and R dot A. Both values must belong to I. Then we say that I is an ideal of R. So here the interesting thing is, if the first property is satisfied and only this property is satisfied and this is not satisfied, in that case also we will say that it is an ideal and we call it as right ideal, because the element R which is taken in the ring is right side of the operation. Since R lies right side to the operation dot, we call it as right ideal. So if this thing is not satisfied and this is satisfied, we say that it is left ideal. So ideal means in general it is both right ideal as well as left ideal. That we need to understand. So we are doing multiplication both the ways, AR and RA. So immediately you can have a question that is there any connection between subring and ideal? So we say that every subring need not be an ideal. Yes, it is just like the property of normal subgroup. Right. So if you take the set Q, the set Z, so Z is subring of Q but not ideal. Because let us say you fix an element in Z, say 5. Here I have taken 1 by 2. So if you consider the product, 5 by 2 does not belong to Z. Okay? So you can say an ideal is a subring. Subring need not be an ideal always. That is one counter example you can take. So Z is just subring, not an ideal. Similarly, Q is subring, not an ideal, just like that. Are you clear now? So on the set I, you are verifying two operations, plus as well as dot. And I will say one more thing, that if you consider the set I and if you take operation plus only, it is just like a subgroup. So if you take the operation plus exclusively on the subset I, then it becomes subgroup of R comma plus. If we say that I is an ideal, that is the advantage of ideal. So ideal is nothing but the additive subgroup for the ring R comma plus. Okay? And immediately, if you want to have a comparison between these two, I will say that you imagine subgroup as an ideal. In group theory, we talk about group, subgroup. In ring theory, we talk about ring ideal. In fact, ideal is just like normal subgroup in the concept of groups. So what I wish to say is, generally, whenever you take a ring, always it will have two ideals. As I have discussed that for every group, there will be two subgroups. Let me say, if you take G is a group, you always say singleton E and G itself subgroups. Similarly, whenever you take a ring, always it will have two ideals, singleton 0 and R itself. So these two, we always call them as trivial ideals or improper ideals. So if you consider any ideal which is in between these two, which is bigger than 0 and smaller than R, that type of ideal, we call it as a proper ideal. So now you can correlate the concept between groups as well as rings. So if you understand group theory clearly, then rings will be very easy. Accepted? The same phenomena we are going to apply here by taking two operations. That's all. Can you recollect this concept of group theory earlier? Say. So you can hear the word trivial, non-trivial, proper, improper, etc. The same thing we are having here. So we can discuss other things that I will give a small result. If you talk of subgroups, is intersection of subgroups is a subgroup? If you talk of words, H1 intersection H2, is it a subgroup or not? Yes. So here also we talk about that. Whenever you take two ideals, the intersection of ideals is ideal. That you can take it as an assignment. I will give an assignment for you. You can ask in the next class if you have any query. And if you talk of union of subgroups, when do we say that union of two subgroups is a subgroup? When do we say that union of two subgroups is a subgroup? Say. I think you have forgot the result that can you observe this result which I have proved earlier? Can you recollect this, all of you? Union of subgroups is a subgroup if and only if one is contained in the other. The same result we will apply here. So, I1 union I2 is an ideal if and only if I1 subset of I2 or I2 subset of I1. Now you can observe the similarity between group theory and ring theory. And one more thing, if you want to write the proof of this thing, the same steps we follow here. Whatever the logic you applied, whatever the steps you have written there, the same steps we apply here. Only condition varies. There you take the condition A dot B, here you take the condition A minus B. That is the only thing in proving it. That's all. The same logic we apply here. So you can take it as an assignment. I give these two problems for assignment for you. You just try. If you didn't get, I will reveal the solution in the tomorrow class. Okay? Is that fine? Right. So another thing is, you talk about the quotient group, isn't it? So there you have written the fact that G by H. So here G is a group, H is normal subgroup. We define G by H as set of AH such that A belongs to G. We call it as quotient group. Here we talk about R by I. R is a ring, I is an ideal. It is called quotient ring. And how do we define this? Set of all A plus I such that A belongs to G. So in group theory, we use the operation dot. In ring theory, we use the operation plus. Here AH is the coset. Here A plus I is the coset. Here identity is H. Here identity is I. Does it make sense for you? The relation between these two? That's it. So at this point, I want to conclude our today's session because we have discussed a lot of definitions. Tomorrow we will go in depth of it. So once you refresh with these contents, as I have given the assignment for you, you just try for it. So tomorrow we will discuss with these things. Right? Thank you very much for your cooperation. And if you have any other queries, you can ask. because ring theory has many definitions. As in when you go for ring theory, after discussing with ideals, we have the concept of homomorphism, polynomial rings, Euclidean rings, principal ideal domains, etc., etc. And at the end of it, you have a field theory separately. It is very vast. So every time you will encounter with different definitions and different concepts always in each class. So it takes time for you to understand all these contents. Okay. If you go at a stretch, we will forget. So I request you that right from today's class onwards, you try to recollect all the definitions in your mind while coming to the class. Then only you will understand other concepts and you can synchronize them. Right?